Okay, we have the spring force and centripetal acceleration homework. This is number 6. This is probably the most challenging problem in this set, so thus the video. It's tricky because we're kind of changing our orientation where we have a wall like here, a surface there, and the normal force that we're dealing with off of that wall is pointing perpendicular to the surface. It's going to be pointing out this way. So that makes things harder. And it's asking for not just calculating a force, but it's asking for calculating a force with regard to the person's weight. So like what percentage of the person's weight or what proportion of the person's weight is the normal force. So we got to find one thing relative to another thing, which is tricky. So thus the video. First of all, let's read the problem, and then we'll go through it and figure out what needs done. We're on this amusement park ride. It's rotating, a big rotating cylinder that you're inside of, and you stick to the wall. The radius of the cylinder is given in the problem, and the frequency of rotation is given in the problem, the number of spins per second. It goes around a little, like for my number, a little more than half of rotation every single second. All right. We're asked to find the normal force in terms of the weight. And remember, weight is also known as Fg, which is also equal to m times g. That's going to come in handy. Then the second part asks us to find mu sub s. As it turns out, I think it's easier to find the second part first, and I'll show you why and how I set it up. There's other ways you could set it up that are like, there's lots of right ways to do it, but I'm going to show you the way that I think is the easiest. So I already mentioned the normal force acting on the guy. Let's draw the other forces. We have gravity acting on the guy, force of gravity, also known as the weight. So that's the W here, the weight. And we have a frictional force, a static frictional force pointing up. Now the guy's not sliding up or down. He is accelerating towards the middle of the circle, so there is a net force to the left, but there's no acceleration up and down. So that tells me that the static friction up is going to equal the gravitational force pointing down. All right, cool. The normal force is going to provide the centripetal force that makes the guy go around in the circle. So the net force is to the middle. In this picture, it's to the left. And it's providing the centripetal acceleration, so the normal force is the centripetal force in this equation. It's also going to be handy moving forward. Now, that force of gravity, the weight, equals the static friction holding the guy up, keeping him from sliding down. We can calculate the static friction using mu s times Fn, and that's equal to the force of gravity, also known as the weight. So part 1 says, what is the normal force with respect to the weight? Well, this is an equation that has normal force on one side and the weight on the other. So we got normal force here and weight on the other side. So I can find whatever this ratio is. I can't get the number yet, but I can find what it's going to be. So normal force, Fn, is going to equal 1 over mu s times Fg, times the weight. So whenever I find what mu s is, 1 divided by mu s is going to go in this box. So the answer to that first box is 1 over mu s. And when we find what mu s is, we can put a number in there and get it. But in the meantime, we've got to find what mu s is. So we're not quite there yet. I'm going to erase some of this to give me a little more space. All right. So we know that the static friction is mu s times the normal force. And that equals the weight, which is equal to m times g. Weight is equal to m times g. Awesome. We also know that the normal force equals the centripetal force in this problem. And the centripetal force is equal to mv squared over r. That's the equation for centripetal force. So I can write mu s times mv squared over r equals mg. All right, cool. The m's divide out. So I'm getting closer to being able to solve for mu s. I know r, that's given in the problem. I know g, that's 9.8. I don't know v. I have to figure that out. So I'm going to find the v by using the frequency. Frequency is the number of rotations per second. I want to get the number of meters per second. That's what v is. So frequency is some number of rotations per second. I'm trying to get to meters per second. So I need to convert from rotations to meters. So I need to know how many meters are in a rotation. One time around the circle. If I want to know how far it is to go one time around this circle, one time around this ride, I need to know the circumference of the circle. And the circumference of the circle is 2 times pi times r. So I take my number of rotations per second and multiply by the radius, and I get the rotations are going to go away, and I get meters per second. And that's going to be the velocity, which I can put into my equation down here. At that point, I know everything except for mu s. I can solve for mu s. Mu s is going to be g times r divided by v squared. So I'll get my number for mu s, and then 1 divided by that number is going to be in my top box, because that's the multiplier by the weight.